My name is Philipp Wellnitz, and in this video, I'm going to talk about joint work with Tomasz Kociołmaka and Jakob Nogler about the communication complexity of approximate, pattern, or string match. Let me start with a small example taken from the daily life of a researcher in theoretical computer science. We, as researchers, typically submit drafts of our research works to conferences such as STOC. Then they get reviewed, and then at some point, a list of accepted drafts comes out. On this slide, you can see such a list of accepted papers. Now, after you found your own submissions on this list of accepted papers, what is the first thing that you do? Right, you check how your colleagues' papers did. So let us do exactly that and search for papers from Saarbrücken in this list. And, well, we find the word Saarbrücken 5 times, highlighted in purple. Unfortunately, we missed some papers of our colleagues because for their papers, somehow the umlaut in Saarbrücken got messed up. I highlighted these Saarbrückens in red. Okay, so what did we see here? Well, we started with the simple task of finding Saarbrücken in a text. However, we realized that finding just the exact occurrences is not enough. We also want to find this variant here, or this variant, or really any of the countless variations that might appear. So formally, we want to solve this problem here, the approximate string matching problem. We are given a text T, a pattern P, and the threshold K, and our task is to find all starting positions of substrings of T that are at added distance at most K to P. Recall that the added distance of two strings is the minimum number of character insertions, deletions, or substitutions to turn one string into another string. Many researchers have studied the approximate string matching problem and its variation. On this slide, I have summarized the current state of the art for the important special case when the pattern is roughly of the same length as the text. This is also the special case that I will be assuming for the rest of the video. I plotted the worst case running time required for different thresholds K. We don't allow any edits, we recover the exact string matching problem for which linear time solutions are present in most algorithms textbooks. This case corresponds to the bottom left corner of the plot. The other extreme in the top right corner is when we allow for an arbitrary number of edits. And this is essentially as hard as computing just the edit distance of two strings. Famously, due to Backus and Indig, any strongly subquadratic algorithm for this case would yield a breakthrough for the satisfiability problem, so we don't believe in it, that such a thing exists. Now, between these two extremes, we see many interesting algorithms. So classically, we have the order of k times n algorithms by Landau and Wishkin, and the order of n plus k to the 4 algorithm by Cole and Harry-Rahn, which was recently improved to n plus k to the 3.5, and which is going to be improved to n plus k cubed soon. Okay, and then there's the lower bound that I mentioned before, and this effectively rules out any algorithms that are faster than n plus k squared. However, what happens in this region with the large red question mark? We don't know. There could be a faster algorithm, or there could be a better lower bound. Okay, let me highlight a little bit why getting rid of this question mark here is a major theoretical challenge. But before that, let us first talk a little bit about the challenges to push k to the 3.5 down to k cubed. If you look at the existing algorithm, it has three main parts, or there are three main parts. First, there's a case when the pattern is in a sense very unstructured, very far from periodic. Then there's a case where a pattern is very repetitive or periodic. And finally, there's an even more fundamental question of how to actually return the output. So for pushing k to the 3.5 to k cubed, turns out that there's actually only just one major challenge, namely the periodic case. The other two cases are already fast enough in a sense. They're already at k cubed. Yeah, so the far from periodic case can be solved in order of k cubed, and the output takes order of k cubed space. And as I mentioned, you can manage to push k to the 3.5 down to k cubed, and this boils down to solving this periodic case in k cubed. And as I said, this is in preparation. However, this is not the focus of this, or this is not the content of this video. Instead, I want you to focus on the fact that if we want to obtain algorithms that are faster than k cubed even, then now we not only have one problematic case, but 3 problematic cases instead. And in this video, we tackle the last and most basic issue, namely the output representation. Yeah? If just writing the output already takes more than, or at least k cubed space, and so k cubed time, then we have no chance of obtaining anything faster. Okay? And in particular, we will see that just order of k times log squared n space is actually enough to store a representation of the output from which we then can reconstruct every approximate occurrence, the pattern in the text. And as it turns out, the structural insights that we obtained along the way are by themselves already useful to obtain new and query optimal quantum algorithms for the approximate string matching problem. But I will not say much about these algorithms in this video. Okay, for formally modeling the output representation of ASM, we rely on single-round one-way communication protocols, or STO protocols for short. Let me quickly explain what that is. Okay. In the first step of the protocol, Alice receives the input. In our case, the text, the pattern, and the threshold. Next, Alice compresses the input and sends the compressed data over to Bob. Finally, Bob computes and returns the output from this data received from Alice. Yeah, in our case, this is the set of k added occurrences of the pattern in the text. Now, the size of such a STO protocol is the size of the data sent in step 3. There are some very easy STO protocols out there. First, Alice can just do nothing in step 2 and just send over to Bob the input as is. Of course, Bob then has to do all of the work to actually compute the output. And the size of this very naive protocol is, of course, n, yeah, the size of text in the pattern, which we assume to be roughly the same length for simplicity here. The other extreme is, of course, that Alice just computes everything already and sends over to Bob the answer or the solution, a set of occurrences. Using a recent result by collaborators and myself, this gives a protocol of size k cubed, which is still too large for our goal of beating k cubed. Now, if we look at these two protocols, then in one protocol Alice does all of the work, the other protocol Bob does all of the work. However, the hope is that we can make both Alice and Bob do some work in order to obtain a smaller size STO protocol. Of course, you may ask why I believe that this might be possible. Well, the answer to that question is just that we know how to do exactly that for important special cases of the ASM problem. First, if we don't allow any edits, we can exploit the famous periodicity lemma to obtain a log n STO protocol. Second, if we allow mismatches, but no insertions or deletions, then there's actually a STO protocol of size k log squared n due to Clifford et al. Now, perhaps a little bit surprisingly, we show how to lift this result for the restricted setting where we have mismatches only to the general ASM problem, to obtain a STO protocol of the same size, order of k log squared n. Let me give you an idea of how we managed to do this. For that, it is instructive to first start with exact string matching. In this case, the classical periodicity lemma tells us that all occurrences form a single arithmetic progression. And log n bits suffice to store a single arithmetic progression and thus all occurrences. Let's see a small example. So say we found an occurrence at position 0. Now we have one occurrence, which is a degenerate arithmetic progression. Now say we found another occurrence at position x. Now we have two occurrences, which in itself is still a degenerate or arithmetic progression. But just from these two occurrences, we can already conclude a certain structure about P. Yeah, namely, P needs to be periodic with period x, where x is just the string of the first lowercase x characters of P. Now let's say we find a third occurrence at position 3x. The periodicity that we obtained just from the occurrences at position 0 and x now actually also implies that there's an additional occurrence at position 2x, and we again have our single arithmetic progression. Okay, let's go back one step. And let's say we find another occurrence at position y. And now something interesting happens. You can actually show that P is now periodic with a string x that has a length greatest common divisor of x and y. Okay, so I claim that this actually helps us, these insights actually help us to obtain a through protocol for pattern matching with mismatches. First, our single arithmetic progression is still good enough to capture all occurrences, but now at some terms of this arithmetic progression, there's actually no occurrence. This means we need to store more than just the arithmetic progression. We also need to store some information where mismatches are located. Now, clearly log n bits are not enough to store for each occurrence also the up to k positions where mismatches occur. Even for one occurrence, this already requires k log n bits. However, as it turns out, we can get away with storing just log n occurrences and their mismatch information. In a sense, some occurrences are more valuable than others. Let's again have a look at a simple example. For now, again without mismatches. Say, we found occurrences at positions 0, x, and 2x. And let's say Alice stores all of them. Next, we find another occurrence at position y. Recall that the periodicity lemma now implies that there are also many more occurrences at position that are multiples of the GCD of y and x. However, Alice does not store all of them. Alice just stores the occurrence starting at position y, not the implicit occurrences. In particular, Alice stores an occurrence only if doing so decreases the greatest common divisor of the set of all stored starting positions. The observation now is, whenever the GCD decreases, it does so by a factor of at least 2. So in total, we store at most log n occurrences. The question now is, of course, how can Bob recover the occurrences that we didn't store? To that end, we construct a graph G sub S with a vertex for each character in P and T, and an edge between characters whenever an occurrence that we stored implies that these characters are equal. Okay, so here this is the graph corresponding to having found P starting at position 0, x, and 2x. And now we additionally add the occurrence starting at position y. but just this one. And now we can easily recover occurrences that we didn't store by following the edges of this graph. So for the second character of P, we can see such a following in purple here. Okay, but again, what about mismatches? As I said, things are a little bit more complicated, but one can show that the previous approach still works. The trick is to also store the mismatched characters in our graph GS. As you can see in the picture, we now also store the character A and C that are different from what the periodicity lemma would tell us these characters should be. Yeah. Note that in particular, we just store A and C and not all of the other characters there, like the circle, the star, or whatever. Yeah. Just store that these characters, we don't need to store these characters, we just store characters that correspond to mismatches. Okay, now another occurrence comes, we add some more edges to our graph. And in total, this then allows us to deduce mismatches also for alignments that we didn't store beforehand. Yeah, again, we just followed the edges of this graph, and now we just have to apply a mismatch whenever we see one. Okay. And if you fill in the details, this then gives the aforementioned theorem due to Clifford. Now, in our work, we also allow insertions and deletions. As you might imagine, that makes things even more complicated. Let me just go over the main challenges that we faced. First, due to insertions and deletions, we lose the nice structure in our graph GS that we still had left from the periodicity lemma. In particular, we cannot rely just on the greatest common divisor anymore. Instead, we measure our progress by what we call black components instead, which are, very briefly speaking, connecting components of GS that do not contain any edit or any red edge that we saw in the previous slide. Maintaining these black components and the number of these black components is, of course, much more challenging now. But this can still be done. Now, after we do all of this, it turns out that in the end, we might have actually missed some occurrences now. Yeah. Previously, we could show that just by storing these log n important occurrences, we can recover all others. This is not really the case anymore, but these are just very few extra occurrences that we then can also deal with. Altogether, we then obtain the claimed result. Finally, let me very briefly talk about the quantum algorithms that we obtain. You can read our main result on this slide, but the gist is that the query complexity is optimal. The computational overhead, not so much. Well, and the time is not optimal because the algorithms are already quite complicated as is. We rely on these 4 tools here. Namely, our new combinatorial insights, where a major challenge is to actually make them fast, like to implement all of these steps that I mentioned earlier efficiently and using few queries. But that is not all. Additionally, we also need the existing approximate string matching algorithm of Charalabopoulos and others from 2020, as well as a recent quantum algorithm for computing a bounded version of the edit distance, as well as a new quantum n to the little o of 1 factor approximation algorithm for edit distance that uses just square root n queries, which in itself is an adaptation of a classic sublinear time algorithm for edit distance. And with combining all of these 4 tools, we then obtain a quantum algorithm that uses essentially square root of km queries, for the important special case that text and pattern are roughly of the same length. And then there are some additional overhead in the time. And for arbitrary length strings, just checking if there's just one occurrence, we can even do even faster, which is 0.2 in our main. Okay. Let me wrap up by recapping the key messages. In this video, you saw some ideas behind our new structural insights that allowed us to obtain a way to store the output just order of k log squared n space. And these insights, with some more work, then also yielded query optimal quantum algorithms. That is all. Thank you very much for staying with me until the end. You can find the full paper on arXiv under this link that you see on this slide.